Hey everyone! Let's kick off today's session with a simple question. Have you ever thought why some things like copper wires let electricity sip through them, while others like rubber cables block it completely? Well, the secret lies in how these materials conduct electricity. We classify solids based on their electrical conductivity or resistivity, denoted by sigma, and rho, where rho equals 1 divided by sigma. Metals are the superheroes here. Their resistivity is as low as 10 to the power minus 8 ohmmeter and conductivity shoots up to 10 to the power 8 Siemens per meter. That's why copper and aluminum make perfect conductors for electric wires. Then we've got semiconductors like silicon and germanium, not too conductive, not too insulating, just right in between, like the Goldilocks zone of physics. And finally, insulators, glass, rubber, plastic, they have such huge resistivity values from 10 superscript 1 to 10 superscript 1 ohmmeters that electrons practically give up trying to move. So in short, metals let current dance freely, semiconductors allow it with effort, and insulators just say no entry. Now, resistivity alone doesn't tell the whole story. To truly understand why some materials conduct and others don't, we must peek at the microscopic world where electrons live in energy bands. Here's the trick. In metals, the conduction band already has free electrons waiting to move. In semiconductors, electrons need a little push, maybe heat or light, to jump across a small energy barrier. And in insulators, that barrier, called the energy band gap, is so huge that almost no electrons make it across. Remember this simple relation, sigma equals n times E times mu, where n is carrier density, E is the electron charge, and mu is mobility. So even if a material has lots of electrons, if they can't move freely, conductivity remains poor. This is why resistivity is just one part of the story. It's the energy band gap that decides who's a metal, a semiconductor, or an insulator. Let's zoom into the semiconductors themselves, because not all are created equal. First up, elemental semiconductors, single element materials like silicon, C, and germanium, G. They're the backbone of every microchip you've ever used. Next, compound semiconductors, where two or more elements combine their powers. For instance, gallium arsenide, GaAs, gives you faster switching. It's what your Wi-Fi and satellites rely on. Others like cadmium sulfide, CDS, and indium phosphide, InP, shine in LEDs and lasers. But that's not all. After the 1990s, scientists got creative with organic and polymer semiconductors. Imagine flexible circuits made from materials like polyaniline or polypyrrole, yes, plastics that conduct electricity. Still, for now, C and G rule the Silicon Valley, literally. They're cheap, stable, and reliable. Okay, time to dive deeper. Where does this band structure come from? According to Bohr's atomic model, a single atom has electrons in discrete orbits, each with a fixed energy. But when trillions of these atoms come together to form a solid, the outermost orbits start overlapping. Imagine a crowd of people all talking at once. These overlapping energy levels merge to form continuous energy bands, and that's where the magic of conduction happens. The valence band is where the outermost electrons live, bound to their atoms. The band just above it is the conduction band, where electrons can move freely and carry current. So whether a solid conducts electricity or not depends on how these bands are arranged, tightly bound, slightly apart, or overlapping. As shown in your diagram, figure 14.1 from the textbook, that's how silicon and germanium's energy bands are positioned at absolute zero. Now let's focus on the key player, the energy band gap, denoted as E sub G. It's the energy difference between the bottom of the conduction band and the top of the valence band. The equation is simple: E sub G equals E sub C minus E sub V. In metals, the two bands overlap. Electrons are like excited partygoers, always ready to move. In insulators, the band gap is huge, several electron volts, meaning no electron has enough energy to jump across. But in semiconductors, Eg is small, roughly 1 electron volt, allowing electrons to hop into the conduction band even at room temperature. That's why your computer doesn't need to be heated to 1000 degrees to work. A little thermal energy is enough to make current flow. So, whether a material conducts or not depends purely on how wide that energy gap is. Let's see what happens when we heat a semiconductor. At absolute zero, the valence band is completely full and the conduction band is empty, no free carriers, no current. But as temperature rises, some electrons gain enough thermal energy equal to or greater than E sub J and leap into the conduction band. Every electron that jumps leaves behind a hole, a sort of positive vacancy, in the valence band. And guess what? These holes behave like particles themselves, moving opposite to electrons and carrying positive charge. As more electrons and holes are generated, conductivity increases. The mathematical relation: N is proportional to E raised to the power negative E sub G divided by 2 kT, where K is Boltzmann's constant and T is absolute temperature. So, in simple words, metals hate heat because resistance rises, but semiconductors love heat because more carriers mean better conductivity. Let's put our understanding into numbers. Compare silicon and germanium. At 300 Kelvin, the energy gap for silicon is 1.1 electron volts and for germanium, it's 0.7. Using a relation sigma proportional to E raised to the power negative Eg divided by 2 kT, we can find their conductivity ratio. Substitute the values. kT equals 0.026 electron volts. So, the ratio sigma of silicon to sigma of germanium equals E raised to the power of negative open bracket 1.1 minus 0.7 close bracket divided by open bracket 2 times 0.026 close bracket. Simplify that and we get e to the power minus 7.69, or roughly 4.6 times 10 to the power minus 4. Meaning, germanium conducts about 2000 times better than silicon at the same temperature. But silicon still wins in reliability and stability, which is why our devices use it. So sometimes, it's not about being the fastest, it's about being the most dependable. So, what have we learned today? Electrical properties of solids depend on their band structure. Metals have overlapping bands, excellent conductors. Semiconductors have small gaps, moderate conductors. Insulators have huge gaps, poor conductors. We also discovered how temperature and energy gaps affect conductivity and how elemental and compound semiconductors shape the technology around us, from solar cells to smartphones. So the next time you touch your phone screen or see a glowing LED, remember, it's all a delicate dance of electrons and holes across invisible energy bands. And that's the beauty of semiconductor physics, turning quantum mechanics into everyday miracles. See you in the next session, where we'll dive into the working of diodes, the simplest yet smartest semiconductor device.